Measuring uncertainty on a classification model using SWAG. Hello everyone, this is the title of the work that is performed by Masoud Atai and Nima Sajidi under the course code ECE 591 Deep Learning. For this presentation, I will go with an introduction with a short one, talking about the dataset, having a look at similar work, looking at the model and SWAG as a methodology, and present the result. Representing uncertainty is crucial for decision-making and particularly machine learning models. Knowing that deep learning models typically lack a representation of uncertainty and provide overconfident and miscalibrated predictions. Bayesian methods provide a natural probabilistic representation of uncertainty in the deep learning field. In this case study, a Bayesian approach, which is SWAG, is used for measuring uncertainty in a model that is implemented for object classification and efficiently approximating the posterior distribution over the weights of neural network. Therefore, the motivation for this work is showing that uncertainty is crucial for decision-making and particularly machine learning models, and also that SWAG can improve generalization as well as performing uncertainty calculations besides prediction in a practical approach on MS-COCO dataset. But before going forward, we have to know what is uncertainty. Ultimately, machine learning models are used to make decisions. Representing uncertainty is crucial for decision-making process. For example, in medical diagnosis and autonomous vehicles, we want to predict against rare but costly mistakes. Deep learning models typically lack a representation of uncertainty and provide overconfident and miscalibrated predictions. The uncertainty in neural networks can generally be classified into two groups. First is data uncertainty, and second is model form uncertainty. The data uncertainty relies on the probability distribution of a dataset, which may be associated with the inherent noise in the data generation or observation process. Therefore, this type of uncertainty is irreducible. The second category of uncertainty is model form, which is due to the lack of confidence in making a prediction by a specific model. From the context of neural networks, this uncertainty may be reduced by generating more representative training data. One of the well-known methods to assess model form uncertainty is the use of Bayesian neural networks, which assumes each trainable parameter of a neural network to be sampled from a joint distribution of all parameters that is conditioned on the training data. By characterizing the trained weights and biases of a neural network with a density, several forward model evaluations may be made for the same set of inputs that are used for generating ensemble statistics, such as mean and confidence intervals for the target variable. The MS-COCO dataset is used for classification of objects in this work. COCO images are taken in the wild and are populated with other objects. As part of dataset preparation, a modified and truncated version of MS-COCO stuff dataset is used for this work. MS-COCO stuff originally includes around 164,000 complex images with dense pixel-level annotations. It involves 80 thin classes, 91 subclasses, and one class as unlabeled with support for instance-level annotations for thin section. In general, the dataset is categorized into two sections of stuff and things, and for each category, it further divides into indoor and outdoor sections. Each indoor and outdoor section has subcategories that makes 12 and 15 further subcategories respectively for things and stuff sections. Furthermore, each subcategory is divided into names and titles for objects that reside into its respective subcategory. The figure on the right shows hierarchy of the MS-COCO stuff dataset. Selected subcategories of MS-COCO stuff dataset are marked in green. To reduce training time, the dataset COCO stuff was truncated to thin section, and from that section, indoor division is selected. Since indoor division consists of 6 different subcategories, the food subcategory is selected for this work. Food subcategory, however, consists of 10 food titles or names with almost 17,000 images in total. To proceed with the dataset, 16,255 images were considered for training and 708 images were considered for validation of the model. Moreover, there were 63,512 annotations for training and 2,835 annotations for validation images in total. To fit the dataset into the model, the images were classified into 10 different folders as it was already shown in the hierarchy of the dataset. However, there were images that could be classified into 2 or more folders. For example, an image with an orange and cake, as you can see as the first image on the left side of the screen. Since such images could impact the detection accuracy and uncertainty in the model, these images were duplicated for each of the classification folders that were holding true for them. It resulted in an increase in the size of the dataset and changed the training and validation size respectively to 20,351 and 904 images. The other Bayesian methods, a similar work, are Markov chain Monte Carlo, or in short MCMC, variational inference, dropout variational inference, and Laplace approximations. Monte Carlo was at one time a gold standard for inference with neural networks. However, it requires full gradients, which is computationally intractable for modern neural networks. Variational inference was suggested for a fitting Gaussian variational posterior approximation over the weights of neural networks. This technique was generalized by two persons named Kingma and Welling, which proposed the reparameterization trick for training deep latent variable models. Multiple variational inference methods based on the reparameterization trick were proposed for deep neural networks. While variational methods achieve strong performance for moderately sized networks, they are empirically noted to be difficult to train on larger architectures, such as deep residual networks. Dropout variational inference, a spike and slab variational distribution were used to view dropout at test time as approximate variational Bayesian inference. Concurrent dropout extends this idea to optimize the dropout probabilities as well. From a practical perspective, these approaches are quite appealing, as they only require ensembling dropout predictions at test time, and they were successfully applied to several downstream tasks. And last but not least in this slide, we have Laplace approximations. It was notably used for Bayesian neural networks where a diagonal approximation was utilized for computational reasons. Later on, diagonal Laplace approximations were proposed to overcome catastrophic forgetting in deep learning. More recently, the use of either a diagonal or KFAC approximation to the Hessian matrix for Laplace approximations was proposed. MobileNet is of class of efficient models for mobile and embedded vision applications based on a streamlined architecture that uses depth-wise separable convolutions to build lightweight deep neural networks. The figure on the right is depicting body architecture of the model based on MobileNet that is used in this study. MobileNet is used as the base model with some modifications for which dense layers and global average pooling 2D were added to reduce the dimensions and connect the bottleneck of the model to proceed with the dense layers and have the output. The parameters of MobileNet were initialized with parameters of MSCOCO. Total parameters of the model are 5,857,994, out of which only 21,888 are non-trainable. The rest are trainable. so the majority of them. Dense layers consist of four layers. The first two layers with 10,024 neurons, one layer with 512 neurons, and finish with another dense layer with 10 neurons. The first three layers are followed with ReLU activations, and the last dense layer with 10 neurons was followed with softmax activation function. The loss function is calculated through categorical cross entropy, and data augmentation was used for training the parameter rotation range, with shift range and zoom range respectively set to 30, 0.2, and 0.2, and horizontal flip set to true. In addition, target size was set to 224 multiplied by 224 pixels. For the methodology, SWAG is used. SWAG, or stochastic weight averaging Gaussian, is a state-of-the-art model that is an art model form uncertainty quantification technique, founded on the concept of stochastic weight averaging, or SWA. It's simple, scalable, and a convenient approach to uncertainty estimation and calibration in Bayesian deep learning, and approximates the posterior distribution of collected weights as a Gaussian distribution conditioned on the training data. By sampling the weights from the distribution and performing an ensemble estimation, both the target estimates and their standard deviations can be obtained. Similar to SWA, it aims to fit a Gaussian distribution over the weights. So it uses the SWA solution as mean, a low rank plus diagonal covariance derived from the weights, and then sample weights from distribution to create a new model. As it was said, SWAG samples several weights during a neural network training to obtain ensemble predictions. Each individual object was processed and then SWAG was applied on the network. The model was pre-trained with 256 batch size for 120 epochs, with each epoch taking almost 4 minutes on a local PC with Intel Core i9 10900X for the CPU, NVIDIA RTX 3090 for the GPU, and 64 GB of RAM size. The trainings were running on the GPU, however. After each epoch, the base model was saved for the reference and later use. Pre-trained model was trained again following previous part of the another following previous part for another 50 epochs with batch size 256 with learning rate of 0.001. And after each epoch, SWAG parameters including weights and average weights and sigma dia were calculated and stored locally. At the test time, we generated 30 random parameters or weights from SWAG parameters, and validation images were tested against these parameters. Each of these 30 SWAG parameters are behaving like models separately.
Three different models were used in this study. The simple form, which is the base model as it is MobileNet, with 4 dense layers that was explained. SWAG 1 that runs a SWAG algorithm on the simple model. SWAG 2 that again runs SWAG on the simple model but with adjusted learning rate and a dropout layer added to it. We were mostly looking for the results of the SWAG models in this study. This slide on the left showing how accurate the network performs regarding training and validation for both pre-training on the first 120 epochs and for both SWAG models for the last 50 epochs from 120 to 170. Validation and training loss of the pre-training model, as it is shown on the right images, started from whopping number of 2 and declined gradually to around 1.5 and 1.3 respectively for validation and training loss at the end of epoch 120 for SWAG 1. Continuing with SWAG 1 results, in a further decrease in loss by zero point 0.1. For SWAG 2, the results are even more promising, with a final loss of 1.4 and 1 for validation and training. This slide shows the accuracy of the three models per classes for SWAG 1, SWAG 2, and simple model. SWAG 2 has higher accuracy and better generalization per class in compared with other models. The total accuracy of simple model is 66%. The total accuracy of SWAG 1 is 65%, and the total accuracy of SWAG 2 is 70%. Confusion matrix of the network for both SWAG 1 and SWAG 2, that is depicting number of correctly predicted images, are illustrated in this slide. The left image is shown the results for SWAG 1, and the right image is for SWAG 2. The diagonal values show the number of corrected classified images, and the rest of the matrix shows the wrongly classified images. For instance, for banana, 86 of images are correctly classified as banana in SWAG 1 model, and 60 of bananas images misclassified as apple. As we can see, SWAG 2 performs better in most of the classes. These images represent a visualization of the pattern that the filter responds to and illustrates how deep convolutional neural networks or convnets really learn and how they understand the images we feed them. Keras is used to visualize inputs that maximize the activation of three filters in the last layer of the mobile net architecture for two different models out of 30 ensembles, one shown at the top and one at the bottom, trained through SWAG 1 on MS Coco Things. To generate these images, we started from white noise and gradually changed it using gradient ascent to reduce the loss of the particular filter with respect to the generated image. By having more training on the network, the patterns in the images could be different. Model interpretability shows how the predictions is related to the features of input image. As it could be seen in this image, the network mostly pays attention to the broccoli and ignores the surroundings. To generate normal gradients, we calculate the gradients of top predicted class with respect to input and clip the pixels lower than 5. Uncertainty chart and prediction accuracy of the network on a sample image is presented here. The images on the right contains different objects from the classification list as it's shown on top of the images. The network has detected apple, banana, and orange from the upper image, and the certainty rate for apple is higher than the other fruits, even though more bananas are presented in the image. In contrast to the upper image, the network has detected more sandwiches than orange in the lower image, and the certainty rate of sandwich is also higher than other objects. This study could be further expanded to following points. If we use more epochs for training of the network, we might reach to the better results, because if we didn't use a well-trained network for this work, uh, if we use a well-trained network or a pre-trained network, we might get better results. Benchmarking the implemented work on different models architecture, for example, efficient net, or maybe the state of the art that newly present in the articles, recent articles. Adjusting hyperparameters to find their impacts on the network and the results. We just in this work we just change the learning rate, but by changing the other hyperparameters, we might reach to better results. Object detection, in addition to classification, to find location and size of objects in the image. In this work, we just consider the classification, but locating the objects in the image also is an interesting concept that we, in the further work, we can uh, go for that. In this slide, you can see the references that we use in this presentation. And thank you for listening to our presentation.